What if we are not the first? What if, long before the first dinosaur ever drew breath, before the great ferns unfurled their ancient fronds, there walked upon this earth beings who looked up at the same stars we see tonight, who wondered as we wonder, who built as we build. The thought settles like morning mist over everything we think we know about our planet's story. We have grown comfortable with our timeline, haven't we? We place ourselves at the pinnacle of Earth's 4.5 billion-year journey, the crown jewel of evolution, the first and only species to achieve what we call civilization. But comfort, like all things, can be an illusion. Consider this. If you could compress all of Earth's history into a single year, human civilization would occupy only the final few seconds before midnight on December 31st. In this vast calendar of deep time, entire epochs stretch like empty months, seemingly barren of the kind of intelligence we recognize in ourselves. But what if those months were not empty at all? What if they held secrets we have simply forgotten how to read? The rocks beneath our feet are libraries, their pages written in minerals and sediments, in the slow accumulation of dust and the patient work of pressure and heat. These stone archives span billions of years, yet they are libraries with missing volumes, gaps where entire chapters of Earth's story have been torn away by wind and water, by the relentless recycling of the planet's crust. In these gaps, in these silences between the stones, what might once have lived and loved and dreamed, we have found the bones of creatures that lived 300 million years ago, pressed like flowers between the pages of shale and sandstone. We have traced the rise and fall of countless species, mapped the ebb and flow of ancient seas, charted the dance of continents across the face of a restless globe. Yet for all our careful excavation, for all our patient reconstruction of the past, we know that we see only fragments, only the tiniest fraction of what once was. The fossil record, that great chronicle of life on Earth, preserves perhaps one species in 10,000 that ever lived. The others simply dissolve back into the elements from which they came, leaving no trace, no whisper, no sign that they were ever here at all. If this is true for the simple creatures whose shells and bones we do find, how much more true might it be for beings of greater complexity, beings whose tools were not bone and shell, but perhaps something more subtle, something that time has long since claimed. We stand at the edge of a possibility that reshapes everything. Not the comfortable certainty of being first, but the humbling wonder of perhaps being latest in a long line of questioners, of builders, of dreamers who looked up at the night sky and felt the same longing that moves through us now. The evidence for such a possibility would not shout from the rocks like the massive bones of dinosaurs. It would whisper, encoded in isotopes and minerals, in patterns so subtle we might mistake them for the random accidents of geology. Tonight, as you drift towards sleep, imagine walking backward through time, past the rise of mammals, past the age of reptiles, past the first forests and the earliest complex life. Keep walking, deeper and deeper into Earth's morning, into epochs with names like poetry, the Devonian, the Ordovician, the Cambrian. In these ancient times, when the very air was different and the sun shone on landscapes that would be alien to our eyes, could intelligence have bloomed like an unexpected flower, flourished for millions of years, and then faded so completely that we cannot even guess at its existence? The question hangs in the darkness like a star we have not yet learned to see. What if we are not the first? What if this Earth has cradled consciousness before, nurtured it, watched it grow and create and wonder, only to see it swept away by the same forces that shape mountains and seas? And if this has happened once, or twice, or a dozen times, what does that make of our own brief moment in the sun? We are about to embark on a journey through deep time, through the weight of years so vast they crush our usual understanding of permanence and change. We will walk among the ruins of worlds that may never have been, and in doing so perhaps discover something profound about the world that is. To imagine such a possibility, we must first grasp deep time, and deep time is perhaps the most alien concept the human mind can encounter. We measure our lives in decades, our civilizations in centuries or millennia. We speak of ancient Rome as old, of the pyramids as ancient, but these are merely yesterday's footprints in the sand of eternity. To understand how a civilization might rise and vanish without a trace, we must learn to think in the language of millions and billions of years, where mountains are temporary and oceans are passing thoughts. Picture this: if human civilization were a single breath, then the age of dinosaurs would be a long summer afternoon, and the time before complex life would stretch back like winter nights beyond counting. In this vast expanse, entire worlds could bloom and fade like flowers in a field we have never learned to see. The Permian extinction, that great dying that claimed 90% of all species, happened 250 million years ago. Before that event, Earth spun through space for 4 billion years, wearing countless faces, hosting countless experiments in existence. During the Carboniferous period, 300 million years in the past, the world was warm and wet, covered in vast swamps where trees grew tall as cathedrals and dragonflies soared with wings the span of hawks. Oxygen filled the air in concentrations we would find intoxicating, creating a greenhouse world where life exploded into forms both beautiful and strange. In such a world, could intelligence have evolved along pathways we have never imagined? Could beings have developed technologies based not on metal and fire, but on the patient cultivation of living systems, on symbiosis with the forests themselves? The Devonian, 50 million years earlier still, saw the first forests take root on dry land, transforming the face of the planet from barren rock to green abundance. Fish learned to breathe air, plants reached toward the sky, and the very atmosphere began its long transformation from the alien breath of early Earth to something approaching what we know today. In the shadows of these first woods, in the quiet pools where life was learning new ways to exist, what opportunities might have opened for minds to develop, for awareness to kindle like fire in the darkness. But deep time is not only about opportunity, it is about erasure. The forces that preserve are matched always by the forces that destroy. Continents drift like leaves on water, carrying their secrets to the bottom of the sea. The ocean floor itself is consumed, sliding beneath other plates in the great recycling system of plate tectonics. Rock that once held fossils, that might once have held evidence of intelligence, disappears into the Earth's molten heart, emerging millions of years later as fresh magma, blank as new paper, carrying no memory of what came before. Erosion works like a patient editor, wearing away mountains grain by grain, washing the debris of ages into the sea. Rivers carve through rock layers that took millions of years to form, exposing ancient surfaces to wind and rain that reduced them to sand and clay. The grand libraries of stone that might have held the records of forgotten civilizations are dismantled page by page, their information scattered to the winds or buried beneath newer chapters in Earth's endless book. Weather itself becomes a force of forgetting. Ice ages advance and retreat like breathing, each glaciation scouring the landscape clean, grinding rock to powder, filling valleys with debris, and rewriting the geography of entire continents. The ice sheets that covered North America and Europe mere thousands of years ago erased nearly every trace of the landscapes that existed before them. Imagine what deeper ice ages might have accomplished, what evidence they might have ground to dust and carried away to the sea. Even the air itself changes over deep time. The oxygen levels that sustain us now are a recent innovation in Earth's history. For most of the planet's existence, the atmosphere was a toxic brew of methane and hydrogen sulfide, carbon dioxide and ammonia. But between these extremes, there may have been intervals of stability, periods when the air was different from ours but still breathable to other forms of life, other kinds of minds. These atmospheric shifts leave their own signatures in the rocks, in the ratios of isotopes that record ancient climates, but they also obscure, creating conditions where organic materials decay rapidly, where the evidence of complex behavior dissolves before it can be preserved. The weight of deep time presses down on all possibilities like water at the bottom of the deepest ocean. Under such pressure, certainties become questions, and the impossible begins to seem merely improbable. When we truly grasp the immensity of the past, when we feel in our bones the crushing vastness of the years that stretch behind us, we begin to understand how utterly a civilization might disappear, how completely a species might be forgotten. And yet, if such forgetting is possible, what else might we have forgotten? Rocks, sediments, and isotopes are like memory banks, yet they also erase as much as they preserve, and in this paradox lies one of the deepest mysteries of our planet's past. Earth remembers everything and nothing, holding some secrets for billions of years, while allowing others to slip away like water through cupped hands. To understand how a civilization might vanish without a trace, we must first understand the strange ways our planet chooses what to remember and what to forget. Consider the memory of stone. In the Grand Canyon, we can read the story of 600 million years written in layers of red sandstone and grey limestone, each stratum a chapter in the long novel of geological time. Here, the Earth has been a faithful chronicler, preserving the tracks of ancient creatures, the ripples of primordial seas, the very chemistry of atmospheres long since blown away by solar winds. Yet even in this most complete of records there are gaps, periods called unconformities where entire epochs have been worn away, leaving blank spaces in the narrative like pages torn from an ancient book. The process of preservation is itself a kind of lottery. For a leaf to become a fossil, for a shell to survive the crushing weight of millions of years, conditions must align in ways both precise and rare. The creature must die in just the right place, where sediments will bury it quickly, where oxygen cannot reach to fuel decay, where the chemistry of water and rock will slowly replace organic matter with minerals, cell by cell, until what remains is a stone portrait of what once lived. Most life experiences no such fortune, most simply returns to dust, becomes part of the soil, feeds new growth, and disappears into the endless cycle of death and rebirth that characterizes our living world. But what if intelligence itself leaves different kinds of traces, signatures written not in the obvious language of bones and shells, but in the subtle dialect of isotopes and chemistry? Our own civilization is beginning to write such signatures.
The carbon we burn, extracted from deposits laid down millions of years ago, is shifting the very composition of the atmosphere, leaving a spike in carbon isotopes that will be readable in ice cores and sediments for thousands of years to come. The plutonium from our nuclear tests, scattered now through the soil of every continent, will remain detectable for longer than our species has existed. These are technofossils of the Anthropocene, markers as distinctive as any dinosaur bone. Yet even these seemingly permanent signatures are subject to Earth's great forgetting. Subduction zones, where oceanic plates slide beneath continents, are planetary erasers, carrying entire sections of ocean floor down into the mantle where they melt and merge with the molten rock below. The evidence of whatever fell to those ocean floors, whatever accumulated in those deep sediments over millions of years, is consumed and recycled, emerging later as fresh volcanic rock that remembers nothing of what came before. In the time since complex life began, perhaps half of all ocean floor that ever existed has been consumed this way, taking with it whatever secrets it might have held. Continental drift itself acts as a shuffler of evidence, breaking apart land masses and reassembling them in new configurations, burying some regions beneath others, lifting ancient seafloors to become mountain peaks where erosion can begin its patient work of destruction. The Himalayas, thrust skyward by the collision of India and Asia, contain rocks that once lay beneath tropical seas, but they also contain gaps, places where the collision ground entire formations to powder, erasing whatever record they might have contained. Ice ages function as periodic amnesias, each glaciation scouring clean vast areas of the Earth's surface, carrying away topsoil that took millennia to form, grinding bedrock to flour, and depositing the debris in moraines and outwash plains far from their origins. The ice sheets that advanced and retreated across North America and Europe during the Pleistocene epoch left behind a landscape scrubbed nearly clean of surface evidence from earlier times. If similar glaciations occurred deeper in the past, and geological evidence suggests they did, what traces of ancient activity might they have erased? Climate itself becomes an editor of Earth's memory. Periods of greenhouse warmth accelerate chemical weathering, causing rocks to break down more rapidly, releasing their constituent elements to be washed away by increasingly vigorous rainfall. Desert periods preserve some things while destroying others, mummifying organisms in dry caves, while sandblasting away surface features with winds that carry abrasive particles across entire continents. Ocean chemistry changes over geological time, shifting between conditions that preserve carbonates and those that dissolve them, creating gaps in the marine fossil record that correspond to these chemical transitions. Even the processes that we think of as preserving can become forms of forgetting. Metamorphism, the transformation of existing rocks under heat and pressure, can erase original textures and compositions, turning limestone into marble, shale into slate, sandstone into quartzite, and in the process destroying whatever fossils or unusual features the original rocks might have contained. Regional metamorphism, occurring during mountain building episodes, can affect areas the size of small countries, wiping clean the geological slate across vast territories.
The result is a planet whose memory is simultaneously deep and shallow, precise and fragmentary. We can read the exact temperature of ancient seas and the oxygen isotopes of fossil shells, but we cannot tell you what happened during the millions of years represented by the gaps between rock layers. We can trace the rise and fall of mountain ranges across hundreds of millions of years, but we cannot account for the countless local features that erosion has carried away to the sea. Earth keeps some memories with perfect fidelity, while allowing others to fade until they become indistinguishable from the background noise of geological processes. And if a civilization arose and fell within one of these gaps, within one of these periods of active forgetting, how would we ever know? Fossilization is rare, almost miraculous, a convergence of circumstances so unlikely that paleontologists estimate it occurs for perhaps one species in 10,000 that have ever lived. Most life dissolves back into dust, returning its atoms to the great cycles of carbon and calcium, nitrogen and phosphorus that sustain the living world. Yet we base our understanding of ancient life almost entirely on this tiny fraction that achieved the geological immortality of stone. What vast library of existence have we never read because its pages were written in flesh that time has claimed? The mathematics of preservation are sobering. A creature must die in precisely the right place, where sediments will cover it quickly before scavengers can scatter its remains, where the chemistry of soil and water will favor mineralization over decay. It must avoid the countless processes that destroy organic matter, the bacteria that break down tissues, the acids that dissolve bone, the physical forces that scatter and crush. It must lie undisturbed while layers of sediment accumulate above it, then survive the compression and heating that transform loose sediments into solid rock, all while somehow avoiding the metamorphism that would erase its delicate structures entirely. Even then, the fossil must be discovered. It must lie in rocks that erosion will eventually expose, in places where human eyes might see and recognize what time has preserved. The vast majority of fossils that do form remain forever buried, locked in rocks that will never see daylight, in layers that lie too deep, or in locations too remote for discovery. We know this because when we do find fossil-bearing formations, they contain far more specimens than we can ever excavate, extending beyond the reach of our tools into rock walls and underground expanses that we can only imagine. Consider what kinds of life are most likely to fossilize and what kinds vanish without a trace. Shells and bones, being already mineralized, have the best chance of preservation. Creatures with hard parts, particularly those that lived in environments where rapid burial was common, dominate our fossil collections. But soft tissues, the flesh and organs and neural networks that actually defined how these creatures lived, are preserved so rarely that their discovery makes headlines in scientific journals. We know the shapes of ancient shells and the structures of fossilized bones, but we can only guess at the colors of extinct flowers, the songs of vanished birds, the complex behaviors that required no hard parts to accomplish. Intelligent behavior, in particular, might leave almost no fossil trace. Tool use among early humans is documented not by preserved tools themselves, which were often made of wood or other organic materials that decay, but by the marks those tools left on bones, by the patterns of wear they created on teeth, by the indirect evidence of their effects rather than their direct preservation. If we can barely reconstruct the tool use of our own ancestors from mere millions of years ago, how could we hope to detect the technologies of species separated from us by hundreds of millions of years? The bias toward hard part preservation means that our view of ancient ecosystems is fundamentally skewed. We know far more about the creatures that built shells than about those that did not, more about the animals that lived in environments favorable to fossilization than about those that inhabited places where decay was rapid and burial rare. Forests, with their acidic soils and rapid recycling of nutrients, preserve almost nothing compared to shallow marine environments with their steady rain of sediments. Yet forests may have been precisely the environments where intelligence was most likely to evolve, where the complex three-dimensional habitat and seasonal changes would have favored the development of memory, planning, and social cooperation. Even among creatures with hard parts, preservation varies dramatically. The fossil record of marine invertebrates, with their shells and easy burial in ocean sediments, is relatively complete. We can trace the evolution of these creatures across hundreds of millions of years, documenting their radiations and extinctions in remarkable detail. But the fossil record of terrestrial vertebrates, despite their bones and teeth, is far more fragmentary. Land animals must die in exactly the right places to be fossilized, usually in river channels or lake beds where sediments accumulate rapidly. The vast majority of terrestrial creatures, even those with substantial skeletons, decompose completely in the oxygen-rich environment of dry land. Now imagine a species whose technology was based not on durable materials, but on biological manipulation, on the careful cultivation of living systems. Such beings might have achieved remarkable feats of engineering, through selective breeding, through the guidance of natural processes, through symbiotic relationships with other species. Their cities might have been living entities, their tools grown rather than forged, their information systems encoded in the genetics of companion organisms. When such a civilization ended, whether through extinction or transformation, it would leave no ruins of stone or metal, no artifacts of clay or glass. It would simply return to the forest, becoming indistinguishable from the natural processes it had learned to direct. The absence of evidence becomes not evidence of absence, but evidence of a different kind of presence, one that worked with the grain of natural systems rather than against it. We look for the kinds of traces our own civilization will leave, the plastic and concrete, the metal and glass that we assume any intelligence must produce. But what if intelligence took other paths, followed other strategies, developed technologies so integrated with living systems that their artifacts would appear to us as nothing more than unusual species distributions, unexplained patterns of biodiversity, subtle anomalies in the genetic record of plants and fungi? The fossil record, magnificent as it is in its preservation of deep time, becomes a library of absence as much as presence. Between the creatures whose hard parts achieved stone immortality lie countless chapters of soft existence, the stories of beings who lived entirely in flesh and neural fire, who may have achieved forms of consciousness we cannot imagine, and technologies we would not recognize. In the silence between fossils, in the gaps where preservation failed, whole worlds may have flourished and faded, leaving behind only the faintest echoes in patterns too subtle for our current methods to detect. Our age leaves plastics, alloys and radiation in the rocks, a new kind of fossil, that speaks not of biology, but of intelligence turned toward the transformation of matter itself. These technofossils of the Anthropocene will endure long after our cities have crumbled, long after our bones have returned to dust. Plastic fragments will persist in sedimentary layers for millions of years, aluminum alloys will oxidize but leave distinctive chemical signatures, and the isotopic fingerprints of our nuclear age will remain detectable in ice cores and ocean sediments for millennia to come. If we can leave such traces, what echoes of a pre-dinosaur society might still whisper from the stones? The signatures of technology are often more subtle than the technology itself.
Our computer chips, marvels of human engineering that contain transistors smaller than viruses, will not survive as recognizable devices, but they will leave behind unusual concentrations of rare earth elements, patterns of purified materials that do not occur naturally in such forms. The concrete of our cities contains fly ash from coal burning, creating isotopic ratios that will distinguish 21st century construction from any rock formation in Earth's history. Even our garbage becomes a marker, with glass and metal objects creating distinctive chemical anomalies in the sediments where they are buried. But perhaps the most telling technofossils we leave are not our intentional creations, but the byproducts of our existence. The carbon dioxide we have released by burning fossil fuels is shifting the isotopic composition of the atmosphere in ways that will be readable in tree rings and ice cores for thousands of years. The sulfur dioxide from our industrial processes creates acid rain that alters the chemistry of soils across entire continents. The nitrogen compounds from our fertilizers are changing the nutrient balance of rivers and lakes worldwide, creating conditions that favor some species while driving others toward extinction. These chemical signatures suggest a different way of looking for ancient intelligence, one that searches not for artifacts but for anomalies, not for construction but for the subtle ways that technology alters the natural chemistry of air and water and soil. A civilization that flourished 300 million years ago might have left traces encoded in the isotopic record of ancient atmospheres, in unusual mineral distributions, in patterns of element concentration that cannot be explained by known geological processes alone. Consider the possibility of a society that achieved advanced metallurgy during the Carboniferous period, when vast forests of giant ferns and early trees were laying down the coal deposits we burn today. The smelting of ores produces distinctive isotopic signatures, ratios of heavy to light elements that reflect the high temperatures and chemical processes involved in refining metals. If such activities occurred on a significant scale, they might have left traces in the sediments of that time, anomalous concentrations of copper or tin, unusual isotopic ratios in lead deposits, patterns that would be difficult to explain through natural processes alone. The rare earth elements that are essential to our electronic devices exist in Earth's crust in dispersed forms, concentrated into economically viable deposits only by unusual geological processes or, in our case, by deliberate extraction and refinement. If an ancient civilization had discovered the useful properties of these elements, their mining and processing activities might have created local concentrations that would appear anomalous to geologists studying rocks from that era. Such signatures would be subtle, requiring sophisticated analytical techniques to detect, but they would be no more subtle than many of the isotopic tracers that modern geochemistry routinely employs to reconstruct ancient environments. Radiation provides another possible signature. Nuclear processes, whether from weapons testing or power generation, create isotopes that do not occur naturally in significant quantities. Some of these artificial isotopes have half-lives measured in thousands of years, ensuring their detectability long after the civilization that created them has vanished. The plutonium-239 from our nuclear weapons will remain identifiable in environmental samples for over 200,000 years, a longer span than modern humans have existed as a distinct species. If an ancient civilization had discovered nuclear physics, traces of their activities might still lurk in certain rock formations, in mineral deposits that formed during their era, waiting for analytical techniques sophisticated enough to detect them. Even more intriguing is the possibility that ancient technology might have been based on principles we have not yet discovered, or materials we have not yet learned to create. Our own technological trajectory, from stone tools to bronze to iron to steel to semiconductors, represents just one possible path among many that intelligence might follow. A civilization that developed along different lines might have left traces that we would not recognize as technological at all. Anomalies in mineral formation, unusual crystal structures, patterns of element distribution that seem geological but actually reflect conscious design. The Earth's magnetic field, recorded in the orientation of iron particles in sedimentary rocks, preserves a record of geomagnetic reversals and variations going back hundreds of millions of years. Large-scale electromagnetic technologies might have left distinctive signatures in this record, brief anomalies in field strength or direction that could not be explained by natural geomagnetic processes. Such signatures would be visible only to paleomagnetic studies of the highest precision, but they would be permanent, locked into the rock record with the same fidelity that preserves the natural variations in Earth's magnetic behavior. The chemistry of ancient atmospheres is recorded in the isotopic compositions of rocks that formed under those skies, in the carbon ratios of organic matter, in the sulfur signatures of evaporite deposits. Industrial civilization would inevitably alter atmospheric chemistry, just as our own is doing, creating isotopic fingerprints that would persist in the geological record long after the sources of those emissions had been forgotten. These signatures might be the most durable evidence of intelligence that any civilization could leave, written not in stone monuments that erosion can claim, but in the very atoms that comprise the rocks themselves. The technofossils of the impossible may already exist, waiting in museum collections, in core samples, in the analytical data from countless geological surveys. They would appear as anomalies, as unexplained patterns that do not fit our current models of how natural processes work.
Perhaps some of the mysteries that already puzzle geochemists, the isotopic ratios that seem slightly wrong, the mineral associations that appear improbable, are not products of unknown natural processes but faint echoes of intelligence that once transformed matter as we transform it today. Before the dinosaurs claimed their long dominion over Earth, vast extinction events periodically reshuffled the deck of life, creating empty spaces in the biosphere where new forms of existence could experiment and flourish. These catastrophes, preserved in the rock record as thin layers of strange chemistry and disturbed sediments, mark boundaries between entire geological periods, moments when the rules of life were rewritten and new possibilities emerged from the ashes of the old. Could advanced societies have arisen in the forgotten intervals between these cataclysms, thriving during calm ages and then vanishing so completely that we mistake their erasure for natural extinction? The pattern of extinction and recovery that characterizes life on Earth creates a rhythm of destruction and opportunity that spans hundreds of millions of years. Every 50 to 100 million years, on average, some catastrophe befalls the biosphere, whether from asteroid impacts, massive volcanic eruptions, or more subtle shifts in ocean chemistry and climate. Each of these events eliminates a significant fraction of existing species, sometimes as many as 90%, creating ecological vacuums that surviving lineages rush to fill. In the aftermath of extinction, evolution proceeds at an accelerated pace, producing new body plans, new ecological strategies, new forms of complexity. These recovery periods, lasting millions to tens of millions of years, represent times of unusual evolutionary opportunity. With established ecosystems disrupted and dominant species eliminated, natural selection can explore possibilities that were previously blocked by competitive exclusion. The mammals that inherited the Earth after the asteroid that ended the Mesozoic era diversified into forms as different as whales and bats, elephants and humans, all within a geological instant of the dinosaurs' disappearance. If such rapid diversification can occur in body form and ecological role, might it also occur in neural complexity and behavioral sophistication? The Ordovician extinction, 450 million years ago, eliminated perhaps 85% of all species when ice sheets advanced and ocean chemistry shifted in ways we still do not fully understand. But before this catastrophe, during the 40 million years of the late Ordovician period, Earth supported diverse marine ecosystems of a complexity not seen before in the fossil record. Predators and prey engaged in evolutionary arms races, developing sophisticated attack and defense strategies. Some organisms achieved sizes and shapes that would not be seen again for millions of years. In this world of innovation and experimentation, might intelligence have had opportunities to develop that were foreclosed when the extinction reset the evolutionary game board? The Devonian extinction, 375 million years ago, struck particularly hard at marine life, but left terrestrial ecosystems relatively intact. This pattern suggests a civilization that had learned to live on land, that had made the transition from aquatic to terrestrial existence before the ocean chemistry changes that drove the extinction. Such beings might have watched from shore as the marine ecosystems that had previously supported the planet's greatest biodiversity collapsed into simplicity. They might have inherited a world where the dominant ecological roles were suddenly vacant, where intelligence could expand into niches previously occupied by other forms of complexity. The greatest extinction of all, the Permian event that ended the Paleozoic era 250 million years ago, eliminated up to 96% of marine species and 70% of terrestrial vertebrates. This catastrophe, triggered by massive volcanic eruptions in what is now Siberia, created conditions so extreme that life itself nearly ended. But the recovery from this near-death experience saw the rise of new groups that would dominate the Mesozoic world, including the ancestors of dinosaurs, mammals, and many modern plant families. The devastation was so complete that it erased not only species, but entire ecosystems, creating a blank slate on which life could write entirely new stories. Yet even this most severe of extinctions was not instantaneous. Geological evidence suggests it unfolded over several 100,000 years, plenty of time for intelligence to recognize the changing conditions and attempt to adapt. A technological civilization facing such gradual environmental collapse might have tried various strategies for survival: underground habitats to escape toxic atmospheres, genetic engineering to adapt to new conditions, even attempts at space colonization using technologies we can barely imagine. The failure of such efforts would leave few traces, particularly if the civilization's final decades were spent in desperate attempts at survival rather than construction of monuments. The silences between these great dyings become pregnant with possibility when we realize how much time they encompass. The interval between the Ordovician and Devonian extinctions lasted 50 million years, longer than the entire Cenozoic era during which mammals rose to prominence. The gap between the Devonian and Permian events spanned nearly 100 million years, time enough for evolution to twice produce all the diversity that exists on Earth today. If intelligence can arise once in the history of life, why not many times in the quiet periods when extinction's scythe was sheathed and experimentation could proceed uninterrupted? The fossil record itself becomes complicit in hiding such possibilities. Mass extinctions are defined precisely by their incompleteness, by the gaps they create in the geological record where sediments were not deposited or were later eroded away. These gaps, called unconformities, can represent millions of years of missing time, periods about which we know almost nothing because the rocks that would have recorded those intervals simply do not exist. A civilization that arose and fell during one of these missing intervals would leave no trace in the stratigraphic record, because the very rocks that might have preserved evidence of its existence were never deposited or were long since worn away. Even when sediments from these intervals do survive, they often represent only brief snapshots of environmental conditions rather than continuous records of biological activity. The preservation of fossils requires specific conditions that may not have existed during periods of climatic stability, when erosion dominated over deposition, when the environments that favor fossilization were rare or absent. A world at peace with itself, climatically and tectonically stable, might support complex ecosystems and even technological civilizations, while leaving almost no geological record of its inhabitants. The extinctions themselves become both destroyers and concealers of evidence. The same processes that eliminate species also destroy the sedimentary environments where evidence of those species might be preserved. Volcanic eruptions that trigger mass extinctions also bury existing rock formations under layers of lava and ash. Climate changes that drive species to extinction also alter patterns of sedimentation, erosion, and preservation. The very catastrophes that might have ended ancient civilizations would also have been perfectly suited to erasing almost every trace of their existence, leaving only the silence where their stories should have been written. Civilizations, like organisms, like stars, like all complex structures in the universe, exist in defiance of entropy, that inexorable tendency toward disorder that governs the behavior of matter and energy across cosmic time. Every act of construction, every moment of organization, every thought itself represents a temporary victory against the forces that constantly work to reduce complexity to simplicity, pattern to randomness, information to noise. Yet entropy always wins in the end, and when we consider the deep timescales over which geological processes operate, we begin to understand how completely the identity of a civilization might be erased, dissolved back into the fundamental chaos from which all order temporarily emerges. The concept of entropy, first discovered in the context of steam engines and thermodynamics, extends far beyond physics into every realm where structure and complexity exist. In information theory, entropy measures the loss of data, the gradual corruption of messages, as they pass through imperfect channels. In biology, it manifests as aging, as the accumulation of errors in cellular machinery, as the inevitable breakdown of the complex molecular systems that sustain life. In archaeology, we see it in the decay of artifacts, the weathering of monuments, the gradual return of all human constructions to dust and rust and scattered fragments. But geological entropy operates on scales that dwarf human experience, wielding forces so patient and persistent that they can erase mountains, redirect rivers, and grind the mightiest constructions to powder so fine it becomes indistinguishable from natural sediment. Consider the pyramids of Egypt, built of massive stone blocks and designed to last for eternity. After mere thousands of years, they show clear signs of weathering, their surfaces pitted by wind-blown sand, their joints widened by thermal expansion and contraction, their foundations gradually sinking into the substrate beneath. If these monuments, protected by one of Earth's most arid climates, decay so visibly over such brief time spans, what hope would any construction have over millions or hundreds of millions of years? The processes of decay accelerate in the presence of water, that universal solvent that can dissolve even the hardest rocks given sufficient time. Rain and groundwater carry away the constituent ions of minerals, leaving behind altered compounds that bear little resemblance to their original forms. Limestone weathers to clay, granite crumbles to quartz and feldspar grains. Even the most resistant rocks eventually succumb to chemical attack. The acid rain produced by our own industrial processes demonstrates how quickly this weathering can proceed when atmospheric chemistry changes, dissolving marble statues and limestone buildings in mere decades rather than millennia. Biological processes contribute their own forms of entropy to the decay of complex structures. Plants grow in the cracks of buildings, their roots expanding with irresistible force, splitting apart masonry that might otherwise endure for centuries. Bacteria and fungi attack organic materials, breaking down wood and paper, leather and textile, returning their carbon and nitrogen to the biogeochemical cycles that sustain living systems. Even inorganic materials are vulnerable to biological decay, as certain bacteria can extract energy from metals, accelerating corrosion and contributing to structural failure. The entropy of information may be the most profound form of forgetting that civilizations face. Languages change over time, meanings drift, writing systems are abandoned and forgotten. The linear A script of the Minoan civilization remains undeciphered despite decades of scholarly effort, its meaning lost when the culture that created it disappeared. How much more completely would a writing system be lost over geological timescales, particularly if it were encoded in materials that decay, or in media that we would not recognize as information storage at all? Cultural entropy manifests as the gradual loss of knowledge and skills that require continuous transmission from one generation to the next. Traditional crafts disappear when their practitioners die without passing on their techniques. Scientific knowledge can be lost when civilizations collapse, requiring rediscovery centuries or millennia later. The concrete formulation used by Roman engineers was forgotten during the medieval period and had to be reinvented during the Renaissance. If such losses can occur over mere centuries in literate societies, imagine what could be forgotten over millions of years, especially in cultures that stored their knowledge in organic materials or in living traditions that left no permanent records. Even the concept of identity itself succumbs to entropy over deep time. Species gradually evolve into new forms, losing their original characteristics through the accumulation of genetic changes. Mountain ranges are uplifted and then worn down to peneplains, their distinctive features erased by erosion. River systems change course, lakes dry up or drain away, coastlines shift as sea levels rise and fall. The very landscapes that might serve as reference points for understanding ancient civilizations are themselves temporary features, subject to transformation over the timescales we are considering. The archaeological record of our own species illustrates how quickly entropy can erase evidence of complex societies. Stone tools survive for millions of years, but the wooden handles that made them useful decay within decades. Bone artifacts can persist for thousands of years in favorable conditions, but organic residues that might reveal their function disappear much more quickly. Settlements built of mud brick or wood vanish within centuries, leaving only post holes or foundation stones to mark their former existence. The Great Library of Alexandria, once containing hundreds of thousands of scrolls representing the accumulated knowledge of ancient civilizations, was destroyed by fire, its contents lost forever, except for fragmentary references in other texts. Metallurgy provides a particularly instructive example of entropy in action. Iron artifacts corrode rapidly in the presence of oxygen and water, often disappearing completely within centuries. Bronze is more resistant but still succumbs to patination and structural weakening over time. Gold, the most chemically stable of metals, can persist indefinitely in certain environments, but it is also soft enough to be deformed by geological processes, its original shape and function obscured by the pressures and temperatures it encounters in the Earth's crust. Even if an ancient civilization had achieved metallurgy, the products of their forges would face millennia of chemical attack, mechanical stress, and thermal cycling that would gradually reduce them to unrecognizable oxide minerals scattered through the soil.
The entropy that governs the decay of matter operates with equal force on the patterns of energy that constitute consciousness itself. Brains decay within hours of death, their delicate neural networks dissolved by the same enzymatic processes that recycle all organic matter. The thoughts and memories that define individual identity, the accumulated wisdom of entire cultures, exist only as fleeting patterns of electrical activity in living tissue. When those patterns cease, when the biological substrates that support them return to dust, the information they contained vanishes as completely as if it had never existed at all. Yet perhaps the most profound entropy is not the decay of structure but the forgetting of meaning. Even if artifacts survive, even if some record of ancient activities persists in the geological record, their significance can be lost if there is no continuity of interpretation to bridge the gap between creation and discovery. The stone circles of Neolithic Europe stand as permanent as any human construction, but their original purpose remains largely mysterious despite thousands of years of speculation. How much more mysterious would be the traces of a civilization separated from us not by millennia but by hundreds of millions of years, whose very existence might be recorded only in isotopic anomalies and mineral distributions that we would interpret as natural phenomena unless we knew to look for evidence of intelligence. Ice and fire, the twin extremes of Earth's climate system, have alternately reshaped the conditions for life throughout our planet's history, creating windows of opportunity and periods of crisis that could shelter civilizations or destroy them utterly. The atmosphere itself has been a restless thing, shifting between compositions that would seem alien to us now, moving through cycles of warming and cooling, oxygenation and stagnation that have fundamentally altered what forms of life are possible at any given time. A pre-dinosaur society might have flourished under climatic conditions now unimaginable, in a world where the very air was different, and the rules of survival followed patterns we can barely reconstruct from the chemical traces they left behind. During the Carboniferous period, 300 million years ago, oxygen levels in the atmosphere reached concentrations of 35% compared to our current 21%. This oxygen-rich world supported giant insects with wingspans of over 2 feet, dragonflies the size of hawks, and millipedes that grew as long as automobiles. The extra oxygen would have been intoxicating to air-breathing creatures, potentially supporting more active lifestyles and higher metabolic rates than are possible today. In such an atmosphere, could intelligence have developed along pathways that we cannot imagine, supported by neural systems that could afford to be profligate with energy in ways that modern brains, constrained by oxygen limitation, cannot match? The greenhouse climates that characterized much of Earth's past created conditions of warmth and humidity that extended tropical zones far beyond their current boundaries. Palm trees grew within the Arctic Circle, crocodiles basked on the shores of polar seas, and rainforests covered regions that are now frigid tundra. These hothouse worlds, sustained by atmospheric carbon dioxide levels many times higher than today's, might have supported forms of civilization adapted to perpetual warmth, to landscapes where seasonal variation was minimal and biological productivity was enhanced by the fertilizing effect of elevated atmospheric carbon. But the climate system has also swung toward extremes of cold that dwarf our recent ice ages. Snowball Earth episodes occurring several times in the Precambrian may have frozen the entire planet's surface, creating conditions so severe that only life in geothermal vents and deep ocean environments could survive. The recovery from these global glaciations would have created opportunities for rapid evolutionary innovation as life recolonized a world temporarily sterilized by ice. Could intelligence have emerged during such recovery periods, in ecosystems rebuilding themselves from scratch, unconstrained by millions of years of established competitive relationships? The chemistry of ancient atmospheres tells stories of worlds where different rules applied to the survival of complex life. For much of Earth's history, free oxygen was scarce or absent, requiring life forms to extract energy through fermentation and other anaerobic processes. But the transition periods when oxygen levels were rising or falling in response to biological innovations or geological events might have created unusual opportunities for organisms that could exploit both aerobic and anaerobic pathways, potentially supporting more complex metabolisms than pure reliance on either system alone. Volcanic winter events, triggered by massive eruptions like those that created the Siberian traps or the Deccan traps, would have plunged the world into darkness and cold for years at a time, disrupting photosynthesis and causing widespread ecological collapse. Yet these same events also released enormous quantities of nutrients and trace elements into the environment, potentially creating conditions for rapid biological innovation once the immediate crisis had passed. A civilization that could survive such catastrophes, perhaps through technological means or behavioral adaptations, might emerge into a world with reduced competition and abundant opportunities for expansion. Ocean chemistry has cycled between oxic and anoxic states, creating periods when vast areas of the sea were essentially dead zones, depleted of oxygen and dominated by hydrogen sulfide-producing bacteria. These anoxic events, preserved in the geological record as black shales rich in organic matter, represent times when marine ecosystems collapsed and were replaced by simpler, more primitive communities. But they also represent times when terrestrial ecosystems might have faced less competition from marine life for nutrients washed from the land, potentially supporting higher levels of terrestrial biodiversity and complexity. The magnetic field that protects Earth from cosmic radiation has varied dramatically over geological time, occasionally weakening or even reversing entirely. During periods of magnetic field instability, the planet's surface would have been bathed in higher levels of radiation, potentially driving evolutionary change at accelerated rates, but also creating selective pressures that favored organisms with enhanced DNA repair mechanisms or behavioral adaptations that minimized radiation exposure. A technologically capable species might have thrived during such periods by developing artificial magnetic shielding or by moving to naturally protected environments like deep caves or dense forests. Sea level changes, driven by the growth and melting of ice sheets and by thermal expansion and contraction of the oceans themselves, have repeatedly drowned and exposed vast areas of continental shelf. During ice ages, sea levels can drop by hundreds of feet, exposing land bridges between continents and creating new terrestrial habitats. During greenhouse periods, rising seas can flood low-lying areas, fragmenting populations and creating island archipelagos where evolutionary isolation can drive rapid speciation. These changing geographies would have created shifting opportunities for the development and spread of intelligence, opening new frontiers while closing others. The position of continents themselves has changed dramatically over the timescales we are considering, driven by plate tectonics that can move land masses thousands of miles over millions of years. During the Carboniferous period, the major continents were assembled into the supercontinent Pangaea, creating vast interior regions with desert climates, but also extensive coastal areas where warm, humid conditions prevailed. The breakup of such supercontinents creates new ocean basins and altered patterns of atmospheric and oceanic circulation, fundamentally reshaping global climate patterns in ways that could either support or stress existing civilizations. Asteroid and comet impacts, while catastrophic in their immediate effects, have also played roles in reshaping Earth's climate over geological time. The Chicxulub impact that ended the Cretaceous period not only caused immediate devastation through the impact winter it created, but also triggered long-term changes in ocean circulation and atmospheric composition that persisted for millions of years afterward. Earlier impacts might have had similarly complex and long-lasting effects, creating new climatic regimes that could support forms of life and intelligence adapted to the altered conditions. Even the Sun itself has changed over geological time, gradually growing brighter as nuclear fusion in its core has altered its internal structure. The Sun that shone on the Precambrian Earth was significantly dimmer than today's star, requiring higher atmospheric greenhouse gas concentrations to maintain temperatures suitable for liquid water.
This faint young sun paradox suggests that Earth's early atmosphere was fundamentally different from anything in our experience, possibly dominated by methane, ammonia or other gases that would be toxic to modern life but might have supported entirely different biochemistries and forms of intelligence. The climate cycles that have shaped Earth's history create a kaleidoscope of possible worlds, each with its own opportunities and constraints for the development of complexity and intelligence. In this vast parade of changing conditions, windows of opportunity have opened and closed countless times, creating moments when intelligence might flourish, and other moments when only the simplest and most adaptable life forms could survive. Each warming, each cooling, each shift in atmospheric composition has rewritten the rules of existence, and in those rewritten rules, other forms of consciousness might have found their brief moment in the sun before the wheel of climate turned once again, carrying their civilizations into the silence of geological time. The sea floor is both a keeper and a destroyer of memory, the final resting place of countless secrets yet also the site of their ultimate erasure. In the abyssal depths, far from the reach of sunlight and the turbulence of surface waves, sediments accumulate grain by grain, preserving records of ancient climates, extinct life forms, and the chemical signatures of events that occurred millions of years ago. Yet these same deep places are also where the Earth's crust is consumed, where tectonic plates slide into the mantle and melt away, taking with them whatever evidence they might have held of worlds that existed before the continents reached their present positions. The ocean covers more than 70% of Earth's surface, and beneath its waters lie sedimentary archives that span hundreds of millions of years. In the deep basins where currents move slowly and deposition is steady, layers of microscopic shells, wind-blown dust, and cosmic particles build up at rates so slow that a human lifetime might add only a few millimeters to the accumulating record. These sediments, when retrieved by deep-sea drilling, reveal the history of Earth's climate in exquisite detail, recording temperature changes, ice sheet advances and retreats, and alterations in ocean chemistry that occurred long before any land-based record was preserved. But the ocean floor is not permanent. The process of seafloor spreading creates new oceanic crust at mid-ocean ridges, where magma wells up from the mantle and solidifies into fresh basalt. This new crust moves away from the ridges like a conveyor belt, carrying with it whatever sediments have accumulated on its surface. Eventually, after traveling perhaps thousands of miles over millions of years, this oceanic crust encounters a continental margin or island arc, and is thrust downward into subduction zones, where it melts and returns to the mantle from which it came. The recycling of oceanic crust means that the oldest ocean floor currently in existence is no more than 200 million years old, formed during the early Jurassic period when dinosaurs were just beginning their rise to dominance. Any oceanic sediments older than this have long since been consumed by subduction, carrying their secrets down into the Earth's interior, where temperatures and pressures reduce even the most complex molecules to their constituent atoms. If evidence of ancient civilizations was deposited on ocean floors older than 200 million years, it has been effectively erased from the surface record, digested by geological processes that leave no trace of what they consumed. Yet the ocean's destruction of evidence is not complete or immediate. Sediments deposited near continental margins sometimes escape subduction through a process called offscraping, where layers of sediment are scraped off the descending plate and accreted to the edge of the overlying continent. These accretionary wedges can preserve oceanic sediments far older than the seafloor on which they were originally deposited, creating windows into ancient marine environments that would otherwise be lost forever. In such preserved fragments of ancient ocean floor, evidence of unusual chemical signatures or anomalous material distributions might still await discovery. The deep ocean trenches, those profound gashes in the Earth's surface where subduction occurs, are themselves archives of a sort, collecting sediments that slide down from the continental margins and accumulate in layers that may never see the surface again. The Mariana Trench, deepest point on Earth, contains sediments that have been accumulating for millions of years, building up deposits that are effectively isolated from surface processes.
If ancient civilizations had activities that resulted in materials being deposited in such environments, those materials might persist in these deepest repositories long after all surface traces had been erased. Submarine canyons carved into continental margins by underwater avalanches of sediment create conduits that can rapidly transport material from shallow coastal environments to the deep ocean floor. During periods of low sea level, when continental shelves were exposed and rivers extended their channels far seaward, these canyons would have been particularly active in moving terrestrial material into deep water environments where preservation conditions are optimal. Evidence of coastal civilizations might have been swept into such deep repositories during catastrophic events, preserving in marine sediments traces of societies that left no record on the now submerged continental shelves where they once thrived. Hydrothermal vents on the ocean floor create unique chemical environments where unusual minerals precipitate from hot, metal-rich waters emerging from the Earth's crust. These vent systems can preserve chemical signatures of ancient ocean chemistry, including trace elements and isotopic ratios that reflect conditions at the time of their formation. If ancient civilizations had industrial activities that altered the chemistry of seawater, particularly in coastal regions where hydrothermal activity was occurring, those alterations might be recorded in the mineral deposits that formed around contemporary vent systems. The preservation potential of marine environments extends beyond simple chemical signatures to include physical artifacts and structures. Shipwrecks thousands of years old have been found in remarkable states of preservation on the ocean floor, protected from decay by cold temperatures, high pressure, and anoxic conditions that inhibit the growth of decomposing organisms. Underwater archaeological sites preserve organic materials that would have vanished completely in terrestrial environments, including wood, leather, and even textiles that retain their original structure and composition. Cold seeps, where hydrocarbons leak from the seafloor, create carbonate formations that can entomb and preserve whatever materials happen to be present when the minerals precipitate. These natural concrete formations have preserved everything from bacterial mats to large vertebrate remains, creating fossil deposits that can persist for millions of years in the deep ocean environment. If ancient technological materials were present at such seep sites, they might become incorporated into carbonate formations that would preserve them indefinitely in the marine geological record. Turbidity currents, underwater avalanches that can travel hundreds of miles across the ocean floor at speeds exceeding 50 miles per hour, have the power to transport large quantities of material from continental margins to deep ocean basins. These currents can carry everything from microscopic particles to boulder-sized debris, depositing their loads in deep-sea fans that preserve snapshots of continental erosion events. Major floods, landslides, or even catastrophic events that destroyed coastal civilizations might have triggered turbidity currents that carried evidence of those societies far out to sea, where it remains buried in sedimentary sequences that have yet to be explored. The ocean's role as both preserver and destroyer creates a complex archive where evidence might exist in unexpected forms and locations. Rather than looking for obvious artifacts or structures, we might need to search for subtle chemical anomalies, unusual mineral associations, or isotopic signatures that reflect the activities of intelligent beings. Such evidence would be dispersed and diluted by marine processes, but it might also be preserved in environments where terrestrial evidence would have been destroyed long ago. The vastness of the ocean floor, with its countless unexplored regions and sedimentary sequences that span geological time, represents perhaps the largest repository of potentially preserved evidence from Earth's deep past. Beneath miles of water, in trenches and basins and sedimentary fans that have never been sampled, there may rest traces of civilizations that thrived when the continents were in different positions, when sea levels were hundreds of feet higher or lower, when the very chemistry of seawater was altered by atmospheric conditions we can barely imagine. Could evidence of a forgotten society rest beneath miles of water, untouched, waiting like whispers beneath the tides? Certain minerals lock away radiation, isotopes, and patterns like coded diaries of time, preserving within their crystal lattices the signatures of events that occurred during their formation, holding secrets that can persist for billions of years in forms so subtle they require the most sophisticated analytical techniques to decode. These mineral archives, scattered throughout Earth's crust in formations both ancient and recent, may already contain evidence of intelligence that we have not yet learned to recognize, anomalies in composition and structure that we dismiss as geological curiosities, but which might actually represent the faint fingerprints of conscious activities that occurred in Earth's deep past. Zircon crystals, among the most durable minerals on Earth, can survive multiple cycles of erosion, sedimentation, and metamorphism while retaining their original internal structure and chemical composition. Some zircons found in Australia are over 4 billion years old, dating to within 500 million years of the planet's formation, making them quite literally the oldest solid materials on Earth's surface. Within these ancient crystals, uranium and thorium atoms decay at precisely known rates, providing absolute dates for the rocks in which the zircons formed. But they also contain trace elements, isotopic ratios, and even microscopic inclusions that record the conditions under which they crystallized, creating time capsules that preserve information about ancient environments in extraordinary detail. The lead isotopes produced by radioactive decay in zircons tell stories not just of age, but of the chemical environment in which crystallization occurred. Anomalous lead isotope ratios, patterns that cannot be explained by normal decay processes alone, might indicate the presence of artificial isotopes or unusual chemical conditions that reflect technological activities rather than natural geological processes. If an ancient civilization had discovered nuclear physics, the isotopic byproducts of their activities might be preserved in zircons that formed in contaminated environments, creating permanent records of artificial radioactivity that could persist for billions of years. Diamonds, formed deep within the Earth's mantle under conditions of extreme pressure and temperature, carry to the surface information about processes occurring hundreds of miles below our feet. But some diamonds contain inclusions of minerals that should not exist at mantle pressures, suggesting complex histories involving recycling of surface materials into the deep Earth. If technological materials had somehow been incorporated into subducting oceanic crust and carried down to diamond-forming depths, they might leave isotopic or chemical signatures in diamonds that would be nearly impossible to destroy through any surface process. Quartz crystals common throughout Earth's crust can trap microscopic inclusions of fluids that were present during their growth, creating tiny time capsules that preserve samples of ancient atmospheres, groundwaters, and hydrothermal solutions.
These fluid inclusions can be analyzed for their chemical composition, isotopic ratios, and even their biological content, providing direct samples of Earth's ancient environments. Artificial chemicals or unusual isotopic signatures trapped in such inclusions would create permanent records of technological activities, preserved within the crystal structure of one of Earth's most abundant and stable minerals. Magnetite and other iron-bearing minerals record the orientation and intensity of Earth's magnetic field at the time of their formation, creating a paleomagnetic archive that extends back billions of years. But this same sensitivity to magnetic fields means that these minerals might also record artificial electromagnetic signatures, unusual patterns of magnetization that reflect technological activities rather than natural geomagnetic processes. Large-scale electromagnetic technologies, such as those involved in metal smelting or power generation, might leave distinctive magnetic fingerprints in iron-bearing minerals that formed in their vicinity. Calcite and other carbonate minerals precipitate from water under conditions that depend sensitively on temperature, pH, and the chemical composition of the precipitating solution. The isotopic composition of carbon and oxygen in calcite reflects these formation conditions, creating geochemical thermometers and chemical indicators that can be read millions of years after the minerals formed. Artificial alterations of local water chemistry, such as those that might result from industrial activities or large-scale construction projects, could create isotopic anomalies in carbonate minerals that would persist as long as the minerals themselves survive. Feldspar crystals, abundant in igneous and metamorphic rocks throughout Earth's crust, can incorporate trace elements in concentrations that reflect the chemical environment during their formation. Rare earth elements, in particular, are incorporated into feldspar in patterns that are diagnostic of the source materials and formation processes involved. Artificial concentration or purification of rare earth elements, activities that characterize modern technology, might create unusual trace element signatures in feldspars that formed in contaminated environments, leaving chemical fingerprints that would be virtually impossible to produce through natural processes alone. Clay minerals, formed by the weathering of primary rock-forming minerals, are particularly sensitive to the chemical environment in which alteration occurs. The layer structure of clays can incorporate a wide variety of ions and molecules, creating chemical records of the solutions from which they formed. Industrial pollutants, artificial isotopes, or synthetic organic compounds present during clay formation would be incorporated into the mineral structure, creating contamination signatures that could persist for millions of years in sedimentary environments where clay minerals are stable. Sulfide minerals, formed in environments where sulfur-rich fluids interact with metals, often contain trace elements that reflect the source of the sulfur and the conditions under which precipitation occurred. Anthropogenic sulfur, with its distinctive isotopic signature reflecting the burning of fossil fuels or the smelting of sulfide ores, creates sulfur isotope ratios that are different from those produced by natural processes. Ancient industrial activities might have left similar signatures in sulfide minerals that formed in contaminated environments, creating isotopic records that would persist as long as the sulfide minerals themselves remain unoxidized. Even the crystal structure of minerals can preserve information about formation conditions through features such as twinning patterns, defect distributions, and trace element zoning. High-temperature industrial processes, rapid cooling from artificial heating, or exposure to unusual chemical environments might create distinctive structural features in minerals that would be difficult to produce through natural processes. Such structural anomalies would be subtle, requiring sophisticated analytical techniques to detect, but they would be as permanent as the minerals themselves. The most intriguing possibility is that evidence of ancient intelligence might already exist in museum collections, in thin sections prepared for petrographic study, in geochemical datasets that contain anomalous values dismissed as analytical errors or contamination. The subtle signatures that advanced technology might leave in mineral archives would not announce themselves obviously, but would appear as statistical outliers, as patterns that do not quite fit the expected ranges of natural variation, as correlations between elements or isotopes that seem improbable but not impossible. Perhaps the strangest anomalies already catalogued by geochemists, the isotopic ratios that seem slightly wrong, the trace element associations that appear unusual, the magnetic properties that do not match theoretical predictions, are not products of unknown natural processes, but echoes of intelligence that once existed on this planet. These mineral witnesses, patient and nearly indestructible, may have been waiting billions of years for us to develop the analytical sophistication necessary to read the messages they contain, whispers in the stones that speak of consciousness and technology in Earth's deep past. When we study ancient mass die-offs, those catastrophic episodes that punctuate Earth's history like sudden silences in a long conversation, we typically ask biological questions: which species survived, which perished, how ecosystems reorganized themselves in the aftermath of devastation. But there is another question that hovers at the edges of these investigations, unspoken but increasingly compelling, as we recognize the complex ways that intelligence can both trigger and respond to environmental crisis. Were these extinctions only biological, or did they also mark the end of forgotten societies whose own activities might have contributed to the very catastrophes that destroyed them? The pattern of mass extinctions in Earth's history shows a troubling consistency. They often involve rapid changes in atmospheric composition, ocean chemistry, or climate that exceed the adaptive capacity of existing life forms. These changes can occur over timescales ranging from thousands to hundreds of thousands of years, fast enough to overwhelm evolutionary responses, but slow enough that intelligence might recognize the approaching crisis and attempt to respond. The question becomes whether any of these ancient environmental catastrophes might have been triggered, at least in part, by the activities of technological civilizations that lacked the foresight or capability to prevent the consequences of their own success. Our own species provides a template for how intelligence might contribute to extinction events. The carbon dioxide we have released by burning fossil fuels is altering global climate at a rate unprecedented in recent geological history. The nitrogen compounds from our fertilizers are creating dead zones in oceans and lakes worldwide. The chemicals we have synthesized are accumulating in food webs and disrupting reproductive systems across multiple species. Our activities have initiated what many scientists consider the sixth mass extinction in Earth's history, demonstrating that intelligence can indeed become a geological force capable of reshaping the biosphere on a global scale.
The Permian extinction, the most severe crisis life has ever faced, involved massive releases of carbon dioxide and methane that acidified the oceans and created greenhouse conditions extreme enough to eliminate most marine ecosystems. The volcanic eruptions of the Siberian Traps are typically blamed for these emissions, but the scale and rapidity of atmospheric change exceed what volcanism alone might account for. Could an additional source of greenhouse gases, perhaps from the industrial activities of a Permian civilization, have amplified the volcanic effects and pushed the Earth system past critical tipping points that volcanism alone might not have reached? The isotopic signatures of carbon released during the Permian extinction show patterns that are difficult to explain through volcanic processes alone. The carbon appears to have come from multiple sources, including what might have been massive releases of methane from oceanic clathrate deposits. But methane clathrates are stable under normal conditions and require specific triggers to destabilize suddenly across entire ocean basins. A technological civilization with activities that warmed the oceans or altered their chemistry might have provided just such triggers, initiating cascading releases of greenhouse gases that volcanic activity then amplified into planetary catastrophe. The Triassic-Jurassic extinction, which cleared ecological space for dinosaurs to rise to dominance, coincides with massive volcanic activity in the Central Atlantic magmatic province. But this event also shows evidence of multiple phases of atmospheric change, suggesting a complex interaction between different sources of environmental perturbation. Could some of these phases reflect the collapse and desperate final activities of a late Triassic civilization, their attempts to maintain their technology in the face of deteriorating environmental conditions, actually accelerating the very processes that would ultimately destroy them? The late Devonian extinctions occurred over several million years in a series of pulses that eliminated many marine ecosystems, while leaving terrestrial life relatively intact. This pattern suggests environmental changes that affected ocean chemistry more severely than atmospheric composition, perhaps reflecting industrial activities that concentrated their effects in marine environment. Ancient civilizations that relied heavily on marine resources, or that disposed of their wastes in oceanic systems, might have triggered the chemical changes that characterized this extinction event, poisoning the very ecosystems on which they depended. Even more intriguingly, some extinction events show evidence of environmental changes that preceded and potentially triggered the more obvious geological catastrophe. The impact that ended the Cretaceous period was certainly devastating, but geological evidence suggests that ecosystems were already under stress before the asteroid hit, weakened by climate change and environmental degradation that made them more vulnerable to the final catastrophe. Could these pre-impact stresses reflect the activities of a late Cretaceous civilization, whose environmental impacts had already begun to destabilize global ecosystems? The recovery patterns following mass extinctions also offer clues about what might have been lost. Typically, extinction events are followed by periods of rapid evolutionary innovation, as surviving lineages diversify to fill vacant ecological roles. But some post-extinction radiations show patterns that suggest more than just biological recovery. The unusually rapid pace of certain evolutionary changes, the appearance of new traits that seem to have no obvious precursors, the development of complex behaviors in groups that previously showed little evidence of intelligence, might reflect not just evolutionary opportunity but also the inheritance of environmental modifications or even genetic alterations introduced by vanished civilization. The chemical signatures of extinction boundaries sometimes include elements and isotopic ratios that are difficult to explain through known natural processes. Iridium anomalies, typically attributed to asteroid impacts, occur at some extinction boundaries where no other evidence of impact exists. Platinum group element anomalies, unusual concentrations of rare earth elements, isotopic excursions that suggest rapid changes in atmospheric or oceanic chemistry, all appear in the geological record of various extinction events. While these signatures have natural explanations, they might also reflect the final traces of technological activities, the last chemical fingerprints of civilizations whose industrial processes contributed to their own demise. The spacing between major extinction events, roughly 26 to 30 million years on average, has led to speculation about periodic astronomical causes such as comet showers or solar oscillation. But this periodicity might also reflect another kind of cycle: the time required for intelligence to evolve, develop technology capable of global environmental impact, trigger ecological crisis and disappear, leaving the biosphere to recover and begin the cycle again. If intelligence is a predictable outcome of evolutionary processes, and if technological intelligence inevitably faces the same environmental challenges that we are confronting today, then mass extinctions might mark not just biological catastrophes, but also the graves of civilizations that lack the wisdom to prevent their own destruction. The fossil record of extinction events preserves evidence of biological crisis, but typically lacks the resolution necessary to detect the activities of intelligent species, particularly if those species represented only tiny fractions of total biomass. The signatures of civilization might be preserved only in the chemical anomalies that characterize extinction boundaries, in isotopic excursions and elemental concentrations that we attribute to natural processes because we cannot imagine alternatives. But if we began to look at these signatures with the possibility of intelligence in mind, if we searched extinction boundaries, not just for evidence of what died but for evidence of what might have lived and contributed to its own dying, we might discover that we are not the first species to face the environmental consequences of our own success. The shadows of civilization in extinction events would be subtle, encoded in chemistry rather than morphology, preserved in the timing and character of environmental changes rather than in obvious artifacts, but they might be detectable to analytical techniques sensitive enough to distinguish between natural and artificial sources of atmospheric and oceanic perturbation. In the boundaries between geological periods, in the thin layers of clay and altered rock that mark transitions between ancient worlds, there might rest evidence that intelligence has risen before, and faced the same challenges that confront us today, leaving behind only the chemical fingerprints of their desperate attempts to survive the crises they had created. Civilizations do not only build, they also dream, imagine, and leave wisdom behind. Yet this most precious legacy may be the most fragile of all, preserved not in monuments of stone or metal, but in the patient accumulation of knowledge that each generation passes to the next. What if such wisdom was written, not in books but in subtle marks on the earth itself, encoded in patterns so vast and persistent that we mistake them for natural phenomena, wisdom now scattered as dust across epochs, waiting for minds sophisticated enough to recognize intelligence in forms they never thought to see. The deepest wisdom of our own civilization lies not in our buildings or machines, but in our accumulated understanding of natural laws, in mathematical relationships and scientific principles that represent thousands of years of careful observation and reason. This knowledge exists primarily as information, patterns of meaning, that have no physical existence, independent of the minds that hold them, and the media that store them. Books decay, hard drives fail, languages change, and are forgotten, but the underlying insights about how the universe works represent a form of treasure more valuable than any material wealth, and infinitely more fragile. Consider how quickly human knowledge can be lost even in literate societies with deliberate preservation efforts. The mathematical techniques of ancient Greek geometers had to be rediscovered during the Renaissance. The engineering principles that allowed Romans to construct buildings that still stand today were forgotten during the medieval period, and had to be puzzled out by later architects studying ruins. The astronomical observations of Mayan astronomers, encoded in calendar systems of remarkable sophistication, became incomprehensible when the cultural context that gave them meaning disappeared. If such losses can occur over mere centuries, imagine what could be forgotten over millions or hundreds of millions of years. Yet perhaps ancient wisdom persists in forms we have not learned to recognize. Modern archaeology has discovered that many seemingly natural landscapes are actually the products of human management, extending back thousands of years. The Amazon rainforest, once thought to be pristine wilderness, shows clear evidence of modification by indigenous peoples who enriched soils, encouraged useful species, and created forest compositions that persist centuries after their management ended. These anthropogenic landscapes represent a form of knowledge storage, with ecological information encoded in species distributions and soil chemistry that can be read by those who understand the language of environmental modification. An ancient civilization, with deep understanding of biological systems, might have stored their knowledge in living archives, encoding information in the genetics of cultivated species, or in the structure of managed ecosystems. Such biological libraries would be self-maintaining, evolving and adapting over time, but retaining core patterns that reflect their original design. The unusual distributions of certain plant species, the presence of agricultural terraces in regions now considered wild, even the genetic signatures of domestication in animals that appear natural, might represent fragments of ancient knowledge systems, biological technologies so sophisticated that we mistake them for products of natural selection. Astronomical knowledge, perhaps the most universal form of scientific understanding that any intelligent species might develop, could be preserved in alignments and patterns that persist far longer than the civilizations that created them. Stone circles and megalithic monuments demonstrate human ability to encode sophisticated astronomical information in permanent structures, but similar encoding might occur at scales we have not considered. Mountain ridges altered to create sight lines for celestial observation, river valleys modified to serve as natural calendars, even the positioning of cities and agricultural areas in patterns that reflect deep understanding of celestial mechanics, could preserve astronomical wisdom in forms that appear entirely natural, unless examined with the right perspective. Mathematical knowledge might be embedded in patterns, even more subtle and persistent. The golden ratio, the Fibonacci sequence, and other mathematical relationships that appear frequently in natural forms might in some cases reflect not just the mathematical nature of physical processes, but deliberate manipulation by intelligence that understood these relationships and incorporated them into large-scale engineering projects. Coastlines modified to exhibit fractal properties, river networks guided to follow mathematical curves, even the spacing of geological features arranged according to numerical sequences, could represent forms of mathematical notion written at landscape scale. The most profound wisdom that any civilization might achieve would be understanding of deep time itself, recognition of the vast cycles that govern planetary and stellar evolution. Such knowledge would necessarily include awareness of the impermanence of technological civilizations, and might lead to attempts at preservation that extend far beyond the survival of the species itself. A truly far-sighted civilization might encode their most important discoveries in the most permanent materials and processes available, accepting that the information would be degraded and scattered over geological time, but hoping that fragments might eventually be recognized and reconstructed by successor intelligence. Isotopic signatures, particularly those involving long-lived radioactive elements, could serve as forms of chemical notation, with specific ratios and concentrations, conveying numerical information to any later civilizations sophisticated enough to decode them. Artificial isotopes with precisely controlled half-lives could function as chemical clocks, marking the passage of time since their creation, and potentially encoding information in their decay products. Such isotopic libraries would be nearly indestructible, surviving metamorphism and even subduction cycles while retaining their essential information content. Crystal structures offer another possible medium for long-term information storage. Synthetic crystals grown under controlled conditions can incorporate trace elements, defects, and structural variations that persist indefinitely under normal surface conditions. Information could be encoded in the three-dimensional arrangement of atoms within crystal lattices, creating storage media that would appear as unusual but not impossible mineral specimens to casual observation, while containing vast amounts of data accessible to sufficiently advanced analytical techniques. Even more speculative, a civilization with deep understanding of biological and geological processes might attempt to encode information in the evolutionary trajectories of life itself, introducing genetic modifications or environmental pressures that would guide the development of later species in specific directions. The unusual intelligence of certain animal groups, the complex behaviors that appear in species with no obvious evolutionary pressure for such complexity, even the emergence of our own species with its unprecedented technological capability, might represent the flowering of seeds planted by earlier intelligence that understood evolution well enough to influence its outcomes across geological time. The dust of forgotten wisdom might be settling around us constantly,
incorporated into soils and sediments, dissolved in groundwater and ocean chemistry, embedded in the genetic code of organisms we consider entirely natural. The unusual concentrations of certain elements in specific geological formations, the isotopic anomalies that puzzle geochemists, the mathematical relationships that appear in landscape features and biological structures, might all represent fragments of an ancient curriculum, lessons in physics and chemistry, and biology and astronomy, that were deliberately preserved in the most enduring media available to minds that knew their time was ending. Perhaps our own scientific discoveries, our recognition of natural laws and mathematical relations, represent not just human achievement, but also the gradual recovery of knowledge that once existed in more complete form, scattered fragments of ancient understanding that we are slowly reassembling into coherent pictures of how the universe works. Our sense of mathematical beauty, our intuition that the universe should be comprehensible to intelligence, our persistent feeling that we are on the verge of discovering something profound about the nature of reality, might reflect genetic or cultural memories of wisdom that was once possessed and then lost, calling us to remember what we once knew but have forgotten. Perhaps Earth itself is not linear but cyclical, caught in vast loops of time where patterns repeat across scales so immense that we mistake the echoes for original sounds, where civilizations may rise, fall and rise again, each unaware of the others, like waves on an ocean that has been breathing the same rhythm for billions of years. In this recursive view of planetary history, identity becomes fluid, memory becomes layered, and the question of whether we are first transforms into the deeper mystery of how many times consciousness has already awakened to find itself alone on a world that remembers everything and nothing. The concept of cyclical time appears throughout human cultures, from the Hindu notion of cosmic cycles lasting billions of years, to the Mayan understanding of nested calendars that track multiple overlapping periodicity. These ancient cosmologies may reflect something more than mythological imagination. They might represent intuitive recognition of patterns that operate at scales too vast for individual human experience to encompass directly. If intelligence has emerged multiple times in Earth's history, separated by intervals of geological time, each occurrence might preserve faint memories of previous cycles, cultural DNA that influences how later civilizations develop their understanding of cosmic rhythm. Geological processes themselves exhibit cyclical behavior across multiple time scales. The Wilson cycle describes how ocean basins open and close over periods of several 100 million years as supercontinents assemble and break apart. These cycles create repeating patterns of climate change, sea level variation, and biological radiation that might provide regular opportunities for the evolution of intelligence, windows of stability, that occur with predictable frequency across Earth's history. If intelligence tends to emerge during specific phases of these geological cycles, then consciousness might be as periodic as the positions of continents or the chemistry of atmospheres. Solar cycles operating on timescales from decades to millions of years create additional periodicities that might influence the probability of intelligence arising or surviving on Earth. The Sun's position relative to spiral arms of the galaxy changes over periods of tens of millions of years, altering the cosmic ray environment and potentially affecting mutation rates and evolutionary pressure. Solar luminosity itself varies over even longer periods as stellar evolution proceeds, creating gradual changes in the energy available to drive biological processes. These astronomical cycles might create a hierarchy of nested opportunities and challenges that shape when and how intelligence can emerge and persist. The magnetic field reversals that periodically flip Earth's north and south magnetic poles occur at irregular intervals averaging several 100,000 years, creating windows of increased radiation exposure that might accelerate evolutionary change while also threatening existing ecosystems. During periods of magnetic field instability, the protective magnetic envelope that shields Earth's surface from cosmic radiation weakens dramatically, potentially creating selective pressures that favor intelligence as a survival strategy, while simultaneously threatening technological civilizations that depend on sensitive electronic systems. Ice Age cycles driven by variations in Earth's orbit and rotation create periodic opportunities for evolutionary innovation as species adapt to changing climates and shifting habitat. The advance and retreat of ice sheets not only destroys existing ecosystems but also creates new ones, opening ecological niches that might be filled by emerging forms of intelligence. These glacial cycles operate on time scales of tens of thousands to millions of years, providing regular environmental disruptions that could serve as evolutionary pumps, accelerating the development of consciousness during recovery period. Even extinction events, despite their apparent randomness, show statistical patterns that suggest underlying periodicities in the processes that trigger them. The approximately 26 million year spacing between major extinction events has been attributed to various astronomical cycles, but it might also reflect the natural rhythm of intelligence itself, the time required for consciousness to emerge, develop technology capable of global environmental impact, trigger ecological crisis and disappear, leaving the biosphere to recover and begin the process again. If consciousness is indeed periodic, then each emergence would occur in a world shaped by the activities of previous cycles but lacking direct memory of them. The atmospheric composition, soil chemistry, mineral distributions and even the evolutionary trajectories of life forms would bear the subtle signatures of earlier intelligence, creating initial conditions that might influence how later consciousness develops. The unusual abundance of certain metals in Earth's crust, the isotopic ratios that seem anomalous for purely natural processes, the genetic sequences that appear to have been artificially modified, might all represent inherited modifications from previous technological civilizations. The recursive nature of such cycles might extend beyond planetary processes to influence the very forms that intelligence takes when it emerges. If consciousness tends to develop along predictable pathways, driven by the same physical laws and environmental pressures, then successive intelligences might independently discover similar technologies, develop comparable social structures, and face equivalent challenges. The convergent evolution of intelligence might produce recurring patterns of technological development that appear across multiple cycles, creating echoes that span geological time. Cultural evolution, operating much faster than biological evolution, but following similar principles, might show its own recursive patterns within shorter time scales. Human civilizations have repeatedly discovered and forgotten the same mathematical relationships, developed and abandoned similar technologies, and faced comparable social and environmental challenges. These patterns suggest that intelligence itself might be attracted to specific solutions, and vulnerable to predictable failure modes, regardless of the historical context in which it emerged. Language evolution shows recursive patterns where similar sounds and structures arise independently in unrelated linguistic traditions. Mathematical discoveries follow convergent paths in different cultures, with concepts like zero, negative numbers and calculus emerging multiple times in human history. Scientific principles are rediscovered by successive generations of investigators, suggesting that the structure of natural law constrains the forms that understanding can take. If these patterns operate within human civilization over mere thousands of years, similar convergences might operate across geological timescales as intelligence emerges and develops repeatedly. The sense of déjà vu that occasionally accompanies human experience, the feeling that we have encountered a situation before even when we know we have not, might reflect something more than neurological quirks. If consciousness itself is recursive, if awareness is a pattern that repeats across scales of time and complexity, then individual minds might sometimes access memories that belong not to their personal histories, but to the deeper history of consciousness itself. Echoes of previous awakenings that resonate through whatever medium preserves and transmits the patterns of awareness. Even our scientific method, with its emphasis on reproducibility and verification, might represent unconscious recognition that truth is cyclical, that valid insights will be rediscovered whenever sufficient intelligence is brought to bear on natural phenomena. The mathematical relationships that govern physical processes, the logical principles that constrain rational thought, the aesthetic criteria that guide scientific creativity, all suggest underlying structures that any intelligence must eventually encounter, regardless of its biological substrate or cultural context. Perhaps our persistent intuition, that we are on the verge of some great discovery, that we are approaching a threshold beyond which understanding will be transformed, reflects awareness that we are participating in a cycle that has occurred before and will occur again. Our technology, our scientific insights, our social developments, might all be following trajectories that previous intelligences have explored, approaching decision points that have been reached before, facing choices whose consequences extend far beyond our individual civilization, into the deeper patterns that govern consciousness itself. In this recursive view of time and memory, we become both first and last, original and echo, pioneers and inheritors of a heritage we cannot directly remember, but which shapes everything we do. The earth beneath our feet becomes not just a stage for our activities, but an active participant in the cycles of consciousness, a planet that has learned to dream, and is dreaming still, each awakening both unique and eternal. Each civilization, both beginning and continuation of a conversation that spans geological time. Looking at ourselves, we see how fragile our own traces are, how quickly the monuments we build with such care begin their patient journey back to dust, how briefly our signals will shine before being overwhelmed by the cosmic background radiation of an indifferent universe. In 10 million years, when new mountain ranges have risen, where our cities now stand and different oceans wash shores we cannot imagine, how much of us will remain? Could we too become an invisible chapter, a ghost society buried beneath new life, as forgotten as we have forgotten others who might have walked this path before us? Consider what would remain of human civilization if we disappeared tomorrow. Our cities, built primarily of steel and concrete, would begin corroding and crumbling within decades. The steel would rust, the concrete would crack as water froze and thawed in its pores, and vegetation would gradually break apart even our most massive structure. Within a few thousand years, most of our buildings would be reduced to rubble, indistinguishable from natural rock formations except for their unusual mineral compositions, and the occasional geometric shapes that resist complete dissolution. Our roads and highways, those confident lines we have drawn across continents, would fare little better. Asphalt would crack and weather, returning to its constituent hydrocarbons and mineral aggregate. Even the roadbeds themselves, carefully engineered and compacted, would be gradually dispersed by erosion and biological activity. Tree roots would find every weakness, frost would exploit every crack, and within millennia the great transportation networks that now connect every corner of human civilization would become invisible, their paths perhaps traceable only through subtle differences in soil chemistry or unusual distributions of gravel. The plastic waste that now accumulates in landfills and ocean gyres represents perhaps our most durable legacy, yet even these synthetic polymers would eventually succumb to ultraviolet radiation, oxidation, and slow biological degradation. Microorganisms are already evolving the ability to digest plastics, and over geological timescales, even these seemingly permanent materials would be incorporated into natural cycles of decomposition and recycling. The plastic bottles and shopping bags that now seem like eternal pollutants would become merely unusual concentrations of carbon compounds in sedimentary layers, requiring sophisticated chemical analysis to distinguish from natural organic deposits. Our electronic devices, those marvels of miniaturization and precision engineering, would leave perhaps the strangest traces. The rare earth elements concentrated in computer chips and cell phone batteries would create distinctive geochemical anomalies, unusual concentrations of neodymium and europium that do not occur naturally in such purified form. The semiconductor materials in our integrated circuits would oxidize and decay, but their elemental signatures would persist, creating patterns of contamination that future geologists might puzzle over if they had no context for understanding our technology. The nuclear waste from our power plants and weapons programs would provide the most persistent signatures of our technological civilization. Plutonium-239, with its half-life of over 24,000 years, would remain detectable in environmental samples for hundreds of thousands of years. Other artificial isotopes from nuclear reactors would create lasting markers of our atomic age, isotopic ratios that could not be produced by any natural process, and which would serve as unmistakable evidence that intelligence had learned to manipulate matter at the atomic level.
Yet even these seemingly permanent markers would face the relentless forces of geological recycling. Subduction zones would carry some nuclear waste down into the mantle, where it would be diluted and dispersed beyond detection. Erosion would scatter contaminated sediments across ocean basins. Ice ages would bury radioactive sites under miles of glacial deposits, grinding and dispersing whatever materials they contained. The isotopic signatures that now mark our nuclear activities would gradually fade into the background radiation of natural processes, becoming increasingly difficult to distinguish from the cosmic ray interactions and natural radioactive decay that continuously occur throughout Earth's crust. Our fossil fuel consumption, which is altering the isotopic composition of atmospheric carbon dioxide, would leave traces in ice cores and tree rings for thousands of years to come. But ice ages would eventually erase most ice core records, and the forests that now record our carbon emissions in their annual growth rings would themselves become fossil deposits, their isotopic signatures preserved in coal seams that future beings might burn for fuel, creating their own atmospheric perturbations while unknowingly releasing the chemical ghosts of our industrial age. The most persistent traces of human activity might be the most subtle, The shifts in species distributions caused by our agricultural practices, the genetic modifications we have introduced into crop plants and livestock, the artificial selection pressures we have imposed on countless organisms from bacteria to megafauna, these biological signatures could persist for millions of years, encoded in the evolutionary trajectories of species that survived our influence. The unusual tameness of certain animals, the global distribution of plants that required human assistance to spread, even the evolutionary adaptations that allowed some species to thrive in human-modified environments, would create lasting patterns that might be detectable to future biologists, sophisticated enough to recognize artificial selection in the fossil record, our written records, the vast libraries of information we have accumulated over thousands of years of literate civilization, represent our most precious legacy and also our most fragile age. Paper decays within centuries under most conditions. Digital storage media fail within decades. Even our most durable inscriptions carved in stone or cast in metal would gradually weather away under the patient assault of rain and wind. The knowledge that represents our species' greatest achievement, our understanding of natural laws and cosmic structure, exists primarily as information patterns that have no permanent physical substrate, dependent on continuous cultural transmission to survive even brief interruptions in civilization. Perhaps most sobering is the recognition that our entire recorded history, the few thousand years of written documentation that we consider the foundation of human civilization, represents only the most recent instant in geological time. If our species survives for millions of years, our current phase of technological development will appear as brief as a lightning flash in the long story of human existence. Future human civilizations might look back on our era much as we look back on the earliest tool-using hominids, recognizing our achievements but viewing them as primitive first steps toward forms of technology and consciousness we cannot imagine. The mirror that our own impermanence holds up to the possibility of earlier civilizations is both humbling and illuminating. If we, with all our technological sophistication and conscious efforts at preservation, would leave only subtle traces after millions of years, how could we expect to find obvious evidence of intelligences that existed hundreds of millions of years ago? The absence of clear artifacts from Earth's deep past becomes not evidence against ancient civilizations, but rather confirmation of the fundamental impermanence that characterizes all complex structures in the universe. Yet the mirror also suggests hope. If our own civilization represents a temporary pattern of organized complexity that will eventually dissolve back into simpler forms, it also demonstrates that such patterns can emerge from apparent randomness, that consciousness and intelligence are natural phenomena that arise under appropriate conditions. If we are destined to become an invisible chapter in Earth's deep history, we may also be part of a recurring story, one expression of a tendency toward awareness and understanding that appears whenever the universe provides sufficient time and stability for complexity to explore its own possibility. In recognizing our own fragility, we might also recognize our kinship with other intelligences that may have faced similar challenges across the vast expanse of cosmic time. The knowledge that we too will someday be forgotten does not diminish the reality of our experience or the value of our discovery. Instead, it places us in a larger context, as temporary custodians of the spark of consciousness that illuminates the universe's exploration of itself, brief inheritors of awareness that we will eventually pass on to other expressions of intelligence in forms and times we cannot predict. We close where we began, with a question hanging in the darkness like a star we have not yet learned to see, but now the question has changed, deepened by the journey we have taken through deep time, and the weight of geological forgetting. What if deep down, Earth holds faint imprints of forgotten civilizations, and we are only beginning to notice? Perhaps our curiosity itself is the echo of lives long past, calling us to remember what was deliberately hidden, what was accidentally lost, what was transformed beyond recognition by the patient editing of stone and wind and water. The possibility settles differently now after we have walked through the mathematics of preservation and the chemistry of forgetting, after we have felt in our imagination the crushing weight of millions of years, and the subtle persistence of isotopic signature. We understand now how completely a civilization might vanish, how thoroughly the evidence of intelligence might be edited from the record of rocks, yet also how certain traces, certain whispers, might endure in forms so subtle we have been reading them as natural phenomena, dismissing them as background noise in the great conversation between matter and energy that we call geology. What if the anomalies that already puzzle our instruments, the isotopic ratios that seem slightly wrong,
the mineral associations that appear improbable, the magnetic signatures that do not quite fit our models, are not products of unknown natural processes but fingerprints of consciousness, faint impressions left by minds that learn to alter the fundamental chemistry of air and water and what if our analytical techniques are already detecting the presence of ancient intelligence but we lack the conceptual framework to recognize artificial signatures when they appear in contexts separated from us by hundreds of millions of years? The search would require new forms of collaboration between disciplines that rarely speak to each other, between geochemists who read the stories written in isotopes and archaeologists who interpret the traces of human behavior, between paleontologists who study the deep past and engineers who understand how technology interacts with natural systems. We would need to develop new statistical methods for detecting artificial patterns in geological data, new ways of distinguishing the subtle signatures of intelligence from the background variations of natural processes. Perhaps most importantly, we would need to expand our definitions of technology itself, moving beyond the assumption that intelligence necessarily produces artifacts recognizable as manufactured objects. A civilization that achieved mastery over biological systems might leave traces encoded in the genetics of species that appear entirely natural, their technologies so elegantly integrated with living systems that we mistake them for products of evolution. A society that understood atmospheric chemistry might have altered global climate through methods so subtle that we interpret their effects as natural climate variations, never suspecting that consciousness guided the processes we study as examples of planetary self-regulation. The implications extend far beyond Earth itself. If intelligence can arise multiple times on a single planet, if consciousness represents a recurring pattern rather than a unique accident, then the universe might be far stranger and more populated than our current search for extraterrestrial intelligence assumes. We have been listening for radio signals, looking for obvious signs of technology, expecting alien intelligence to announce itself in forms we would immediately recognize. But what if intelligence typically develops along pathways that leave only subtle traces, signatures so integrated with natural processes that they appear invisible to observers who have not learned to recognize consciousness as a geological and astronomical force? Our own activities are already demonstrating how intelligence can become a planetary phenomenon, altering atmospheric composition, ocean chemistry and even the evolutionary trajectories of countless species. The carbon we release, the isotopes we create, the genetic modifications we introduce, are writing signatures in Earth's geological record that will persist for millions of years. These technofossils of the Anthropocene show us what to look for in the deep past, but they also suggest that we should search not just for direct artifacts but for the broader environmental modifications that intelligence inevitably creates as it grows in scope and capability. The recursive nature of time itself adds another layer of mystery to the search. If consciousness has emerged before, if technological civilizations have risen and fallen in cycles too vast for individual awareness to encompass, then we might be participating in patterns that extend far beyond our species, or even our geological era. The mathematical relationships we discover, the scientific principles we uncover, the aesthetic criteria that guide our creativity, might represent rediscovery of insights that have been found and lost and found again countless times across cosmic history. Perhaps our sense that we are approaching some threshold of understanding, that we are on the verge of breakthroughs that will transform our relationship with the universe, reflects not just human progress but also our unconscious recognition of patterns that have played out before. Our technologies, our scientific methods, our philosophical insights might all be following trajectories that previous intelligences have explored, approaching decision points that have been reached before, facing choices whose consequences extend far beyond our individual civilization, into the deeper structures that govern consciousness itself. The question of whether we are alone in the universe transforms when we consider the possibility that we might not even be alone on our own planet, that consciousness might have roots reaching back through geological time to origins we have never imagined. The Fermi paradox, which asks why we do not see evidence of extraterrestrial civilizations, might have a different answer than we have considered. Perhaps we do see such evidence, but we have not learned to recognize intelligence when it appears in forms that differ from our expectation, when it leaves traces so subtle or so ancient that we mistake them for natural phenomena. Our children, or their children, might develop analytical techniques sophisticated enough to read the chemical signatures of ancient intelligence, to distinguish artificial isotopic patterns from natural variations, to recognize in the deep structure of minerals and sediments the faint fingerprints of minds that thought and dreamed, and struggled with problems not unlike our own. They might discover that the earth beneath their feet is not just a stage for consciousness but a participant in consciousness, a planet that has learned to think through the beings that emerge from its surface, each awakening both unique and part of a larger pattern that spans geological time. The search for our predecessors would also become a search for ourselves, an exploration of what intelligence is and what forms it might take, what traces it leaves and what purposes it serves in the larger evolution of complexity in the universe. We might discover that consciousness is not an accident of biology but a fundamental tendency of matter and energy, a pattern that emerges whenever sufficient complexity and stability coincide, a process by which the universe explores its own possibilities and perhaps remembers its own path. In the end, the question of whether we are first becomes less important than the recognition that we are participants in something larger than our individual species or planet, or moment in cosmic time, whether we are pioneers or inheritors, whether our discoveries are original insights or recovered memories, whether we stand alone or among a vast community of intelligences separated by gulfs of space and time, we remain part of the universe's exploration of itself, temporary expressions of the curiosity that drives matter to organize itself into patterns, complex enough to wonder about their own existence. The darkness that surrounds our brief moment of awareness might not be empty after all. In the vast silences between, in the deep time that stretches behind and ahead of us, in the patient stones that record the history of our world, there might wait evidence of other sparks of consciousness that have illuminated the cosmos, other expressions of the wonder that moves us, to ask questions whose answers might transform our understanding of what it means to be aware in an apparently infinite universe. And perhaps in asking these questions, in developing the tools to search for traces of ancient intelligence, in expanding our conception of what consciousness might become, we are also creating the conditions for our own eventual rediscovery, ensuring that future intelligences will find evidence of our existence, not just in the crude artifacts we leave behind, but in the questions we learn to ask and the methods we develop to seek their answer. Contributions to an ongoing conversation about consciousness and cosmos that might extend far beyond the brief moment we call human history into futures we can imagine but will never see.